Good afternoon, everyone. My name is Irina Francis, working as the cybersecurity analyst in Glorosh Consultancy, Mangalore. Today, I'm going to talk about the project Centralized AI-based overseas recruitment and worker protection system. And my focus is on the cybersecurity and risk intelligence component, where I designed AI-based models to detect recruitment fraud, identify scam communication using NLP, and detect anomalies in visa and financial patterns while ensuring data privacy and compliance with the DTHR Act 2023. Starting off with the uh, presentation. Now, India's overseas workforce plays a critical role in strengthening the national economy through foreign remittances, global employment mobility, and skill exports. However, the overseas recruitment ecosystem is increasingly threatened by systematic cyber cyber enabled crimes, including illegal recruitment practices, visa trading, human trafficking networks, forged documentation, cyber harassment, and the exploitation of vulnerable job seekers, particularly youth from Kerala and other high migration regions. Now, the centralized AI based overseas recruitment and worker protection system is mainly proposed as a national cybersecurity-driven governance framework designed to eliminate illegal intermediaries, secure migrant data, and ensure ethical, transparent, and compliant overseas employment processes. Now, this model mainly explains the issues: fake WhatsApp and Instagram job scams, unregistered recruitment agents, visa trading networks, forged documents, data misuse of migrant workers. Now, this is the literature review uh, done based on this research. The literature review focuses mainly on AI/ML based recruitment fraud detection and cybersecurity frameworks. Existing research shows that supervised learning, deep learning, and NLP models are effective in detecting fake job postings, scam messages, and abnormal patterns. And techniques like anomaly detection and graph based analysis are also used to identify evolving fraud activities. However, most studies focus only on detection models and lack integration with cybersecurity architecture, data privacy, and legal compliance. The white papers and authoritative sources highlight the importance of zero trust security, IAM encryption, and regulatory frameworks like the DPTP Act 2023. Now, based on this, the literature identifies a gap in developing a unified, security-centric AI system, which might which the project addresses by combining AI models with cybersecurity and compliance mechanisms. Now, the model, talking about the model development, three models is mainly focused on developing at the end of this research phase, which they are recruitment fraud classification model. Second is the NLP based scam pattern detection model. Third is the anomaly detection model for visa and financial patterns. The data set used in Model 1 and Model 3 is UNSW-NB15 dataset, which is a widely used cybersecurity dataset for intrusion detection and fraud analysis. It was created to stimulate a real-world network traffic, including both normal and malicious activities. Some of the features in this dataset are DUR, which is the duration of connection; proto, which is the protocol type; service, which is the network service; SPKTS, which is the source packets; DPKTS, which is the destination packets; SBIS, which is the data sent; and DBIS, which is data received. And like this, almost 42 features is there in this data set. And for model 2, a custom data set was built consisting of recruitment related messages. This is the overall workflow diagram of this project, starting from the data sources, then the data collection, then we're doing the data preprocessing, feature engineering, and we're creating three models. Then the risk aggregation is happening, and security decision engine, finally to audit and compliance logs. First, Starting with the first model, which is the recruitment fraud classification model. This is mainly done from fake job postings, visa fraud patterns, and identity misuse. This model, whether a recruitment activity is normal or fraudulent, and this is used by supervised learning, which uses structured data from the UNSW NB15 cybersecurity dataset. Here, the data is preprocessed and converted into numerical format. A neural network learns patterns of normal and attack behavior. Final layer uses sigmoid function output, which is like 0, the labeled one if it's 0. If the labeled one is a 0, it is normal activity, 1 is fraudulent activity. Now we have achieved 96% accuracy. Talking about the classification report of the model 1, the confusion matrix shows the performance of the fraud classification model by comparing actual and predicted values out of the total samples. 700 and 180 normal instances were correctly classified as normal, while 8,608 fraudulent instances were correctly identified as fraud, indicating strong detection capability. However, 238 normal cases were incorrectly classified as fraud, which is the false positives, and 441 fraud cases were misclassified as normal, which is known as the false negatives. These misclassifications are uh, relatively low compared to the total data set, showing that the model performs reliably. The classification report further validates the model's effectiveness. For class 0, which is normal, the precision is 0.94 and recall is 0.97, indicating that most normal cases are correctly identified with minimal false alarms. For class 1, which is fraud, the precision is 0.97 and recall is 0.95, showing that the model is highly effective in detecting fraudulent activities. The F1 score for both classes is around 0.95 to 0.96, indicating a good balance between precision and recall. The overall accuracy of the model is 96%, which confirms that the model performs consistently well across the dataset. These results demonstrate that the fraud detection model is both accurate and reliable for real world applications. The accuracy graph, which received after the Model 1 implementation shows that both training and validation accuracy increases steadily over epochs, indicating that the model is learning effectively from the data. The training accuracy improves from around 89% to approximately 96%, where the validation accuracy also follows a similar trend and stabilizes around 95 to 96%. The close alignment between training and validation accuracy suggests that the model generalizes well to unseen data and does not suffer from significant overfitting. This indicates that the fraud classification model is reliable and performs consistently on both training and validation sets. Now, talking about the loss graph from implementation of Model 1 shows a consistent decrease in both training and validation loss as the number of epochs increases, indicating that the model is reducing prediction errors effectively. The training loss drops from around 0.24 to nearly 0.10, while the validation loss also follows a similar decreasing pattern with minor fluctuations. The closeness of two curves suggests that the model is not overfitting and maintains good generalization performance. Overall, the decreasing trend in loss confirms that the model is learning meaningful patterns for accurate fraud detection. Next one is the model 2, which is the NLP based NLP based scam detection model, which is done from social media scam pattern analysis. This model analyzes recruitment messages to detect scams. uses text data such as job messages, emails, or alerts, and includes real-time user input interface. Messages are converted into numerical form using TF-IDF. Neural network identifies scam-related keywords like urgent, visa, payment, model, and the model predicts probability of scam. So mainly, so in this user input, if we type the messages, the model gives an output or model predicts if the message is legitimate, suspicious, or scam. If it's less than 30 percentage, then it is legitimate message. 30 to 70 percentage, it is suspicious, and if it is greater than 70 percentage, it is scam. Uh, Talking about the confusion matrix, confusion matrix shows that the model correctly classified five legitimate messages and four scam messages. However, two scam messages were incorrectly classified as legitimate, while no legitimate messages were misclassified as scams. This indicates that the model is very good at identifying legitimate messages but slightly less effective in detecting all scam messages. The classification report further explains that the model's performance for legitimate messages, the precision is 0.71 and recall is 1, meaning all actual legitimate messages were correctly identified, but some scam messages were mistakenly predicted as legitimate. The accuracy graph shows that the training accuracy steadily increases from around 58% to nearly 100 percentage, indicating that the model is learning the training data very effectively over epochs. At the same time, the validation accuracy improves from about 60 percentage to around 80 percentage and then stabilizes, which means the model is able to generalize reasonably well to unseen data but not perfectly. The gap between training and validation accuracy suggests slight overfitting, mainly due 63 to the small data sets. Overall, the graph confirms that the model successfully learned scam related patterns, but its performance on new data can be further improved with more training data or regularization techniques. The loss graph shows that the training loss decreases steadily from around 0.69 to approximately 0.08, indicating that the model is continuously improving and reducing errors on the training data. Similarly, the validation loss also decreases from about 0.69 to around 0.41, which means the model is learning useful patterns that generalize to new data. However, the training loss is significantly lower than the validation loss, indicating that the model performs better on training data than on unseen data. Next, the TF-IDF word importance graph highlights the most influential words used by the model to detect scam messages. Words such as job, visa, interview, fee, and payment have higher TF-IDF scores, indicating that they play a significant role in classification. These terms are commonly associated with recruitment-related communication, especially in fraudulent contexts, where phrases like visa processing fee or urgent job offer are frequently used. The presence and importance of such words help the model distinguish between legitimate and scam messages. This visualization improves interpretability by showing how specific keywords contribute to the model's decision-making process. Next model is the anomaly detection for visa and financial patterns. This model detects unusual or suspicious system behavior, works without label data, which is done by unsupervised learning, learns normal behavior patterns, and calculates the reconstruction error. If the reconstruction error is low, it is normal, and if it's high, the anomaly is detected. And final as the result, over 4,000 plus anomalies were detected. The This is the structure of the autoencoder. The architecture shown Here represents the structure of the autoencoder model used for anomaly detection. The model consists of an input layer with 42 features, which corresponds to the number of attributes in the dataset. This is followed by a series of dense layers forming the encoder and decoder. The encoder compresses the input data from 42 features to 32 neurons and further to 16 neurons, creating a compact representation of normal behavior in the latent space. The decoder then reconstructs the data by expanding it back from 16 to 32 neurons and finally to 42 neurons, matching the original input dimension. The model contains a total of 3,834 trainable parameters which are optimized during training to minimize reconstruction error. Since the model is trained to accurately reconstruct normal data, any input that results in high reconstruction error is considered anomalous. This is the reconstruction error distribution graph, and this graph shows how the autoencoder model performs in reconstructing input data. Most of the data points are concentrated near very low error values, indicating that the model is able to accurately reconstruct normal system behavior. A small number of data points extend toward higher error values, representing abnormal or anomalous activities. The vertical threshold line separates normal and anomalous data, where values below the threshold are 67, and which is considered normal, and those above it are figured as anomalies. This distribution confirms that the model effectively learns normal patterns and distinguish unusual. The methods used are data collection, next data pre-processing for extraction and preparation. In that, data cleaning is done, data integration, data transformation, data reduction. Third one, model development, model evaluation and security validation. The model evaluation is as seen before, it's done by accuracy, precision recall, F1 score, confusion matrix and visualization graphs. Uh, Talking about the limitations of the models and project, limited data set was there, and model 1 works only in structured data. Models are not fully integrated into one system, and mainly we are heading forward to integrate all the models into a single centralized system and to deploy on government platforms and to use real world data sets from cybersecurity logs and complaint systems and develop a mobile user interface for real time access. With this, I conclude the presentation. Thank you so much.